Have you ever stopped to wonder about the invisible magic that's happening inside your phone? You know, the tech that lets you steer a race car just by tilting the screen, or keeps a drone perfectly steady in midair. Well, it's not magic. It's engineering. And a huge piece of that puzzle comes down to one tiny, absolutely brilliant component. Today, we're diving deep into the world of the gyroscope sensor to figure out how it works and why it's such a game changer.
So let's just start with the most basic question. When you pick up your phone and rotate it, how does it know? The secret is a microscopic sensor that's constantly measuring pitch, roll, and yaw, which are just fancy terms for the three ways an object can rotate. And that, right there, is the gyroscope in action, turning your real-world movements into digital commands. Okay, let's nail down a quick definition. A gyroscope sensor is a device built specifically to measure something called angular velocity. Now, in simple terms, that just means it doesn't care how fast you're moving forward or backward. It only cares about how fast you're turning or rotating. This is the absolute key to understanding an object's orientation in space.
Now, this right here is a super common point of confusion, so let's clear it up. People mix up gyroscopes and accelerometers all the time. An accelerometer, as you can see, measures straight-line movement, moving up, down, left, right. It tells your phone where it's going, but a gyroscope, it measures rotation. It tells your phone how it's oriented. They almost always work together, but they're measuring two fundamentally different things.
So here's our game plan for this explainer. We're going to start with the classic physics, think spinning tops. Then we'll see how engineers pulled off the incredible trick of shrinking that idea down onto a tiny chip. We'll take a peek inside that modern sensor to see what makes it tick. And finally, we'll wrap up by looking at why this little piece of tech matters so much in our world today.
All right, to really get what's happening in our pockets, we've got to go back in time and look at their much bigger mechanical ancestors. The physics behind them is timeless, and honestly, it's just really cool.
Take a look at this classic design. Right at the heart of it, you've got a spinning disc called a rotor, and it's mounted inside these special pivoted rings called gimbals, which basically give it total freedom to rotate in any direction it wants. The whole thing is then held by a frame. It's a really elegant structure, and it's the secret to its amazing abilities.
And here is the secret sauce. It's not some complicated machine. It all comes down to a fundamental law of physics, the conservation of angular momentum. The basic idea is once something is spinning, it really wants to keep spinning along that exact same axis.
And this is where it gets really interesting. A super fast spinning rotor, like you see in the first part of this image, has a ton of angular momentum. Because of that conservation principle, it fiercely resists any attempt to change its direction. It just wants to stay pointed the same way. You can see it in part 3. Even when you hang it from a string, it seems to defy gravity, holding its orientation perfectly. This principle is so stable that it's literally used to keep satellites and spacecraft pointed in the right direction.
Okay, so we've got this amazing mechanical device that depends on a big, heavy spinning wheel. But how on earth do you take that and cram it into the impossibly thin design of a modern smartphone? Right, this was the billion-dollar question for engineers everywhere. You can't just build a microscopic spinning top with tiny little gimbals. I mean, it would be wildly impractical, and it would probably just shatter the first time you dropped your phone. So a completely new and much cleverer approach was needed.
And wow, this comparison really puts the whole thing into perspective, doesn't it? On the left, you see the beautiful, complex, and, well, bulky mechanics of a traditional aircraft gyroscope. And on the right, that tiny little black square is its modern equivalent. The scale of this miniaturization is just staggering. So how'd they do it?
The answer has a name, MEMS, which stands for Micro-Electromechanical Systems. And here's the crucial point, the big twist in the story. To shrink the gyroscope down, engineers had to throw out the spinning rotor entirely. Instead of spinning, the modern gyroscope vibrates. This wasn't just a small change. It was a complete reinvention of the idea.
So let's pull back the curtain and go inside that tiny chip. We're about to find out how a vibrating structure can possibly tell you which way you're turning. This is where the real genius is.
So if it's not angular momentum anymore, what's the new physics principle? Well, it's something called the Coriolis effect. You've probably heard of it on a huge scale. It's what makes hurricanes spin. But it also works on a microscopic level. The idea is this. When a tiny mass is vibrating back and forth, and you suddenly rotate the whole system, a new force appears out of nowhere and pushes that mass sideways. That tiny, almost undetectable push is everything.
And this image shows the incredible microengineering behind it all. You have these structures they call driving forks that are electrically charged to create this constant, super stable vibration. That vibration moves the bigger, driving mass. But look right there in the center. That's the sensing mass, and it's designed to be able to move sideways, perpendicular to that main vibration. The whole thing is suspended on these impossibly thin elastic beams.
Okay, so here's how this little masterpiece works, step by step. First, those driving forks create that constant, predictable vibration. Now you turn your phone. That rotation introduces the Coriolis effect, which generates a force that pushes that sensing mass sideways. Now this movement is microscopic. We're talking nanometers, but it's just enough to change the distance between the sensing mass and some fixed plates underneath it. That tiny change in distance alters their electrical capacitance, which an onboard circuit detects instantly. And just like that, that change is converted into a digital signal that tells your phone exactly how fast and in what direction it's rotating. It's an absolutely genius solution. Now that we've geeked out on the incredible mechanics inside, let's pull back and look at the big picture. Why these tiny, vibrating sensors have become so incredibly important in our modern world. So, for an engineer, picking one of these sensors, these specs are everything. But they're not just numbers. They translate directly into your experience. How sensitive is it? Can it pick up the tiniest little tilt? How stable is it over time? That's what we call drift. Without good stability, your phone's screen might look like it's slowly turning all by itself. How fast can it respond? That's bandwidth. All of these things determine if a sensor is good enough for a simple game or if it's reliable enough for life-saving medical gear.
The advantages of this MEMS approach are what made them blow up. They're ridiculously small and light, they're incredibly reliable because there are no big moving parts to wear out or break, and they barely use any power, which is absolutely critical for all our battery-powered gadgets. This combination is what unlocked the entire world of motion-aware technology we pretty much take for granted today.
But hey, they're not perfect. MEMS gyroscopes are prone to that drift we mentioned, where tiny little errors can add up over time. They can also get thrown off by temperature changes, and they need to be calibrated carefully to be accurate. And this is exactly why they are almost always paired up with an accelerometer in one single package. That package is called an IMU, or Inertial Measurement Unit. The two sensors basically cross-check each other, correcting for errors and giving a much more accurate picture of what's really happening.
And you'll find this technology way beyond just our phones and drones. Think about the electronic stability control in your car that helps stop you from skidding on an icy road. It's using a heavy-duty gyroscope, like the one you see here, to instantly detect when the car is starting to spin out so it can apply the brakes and get you back in control. They're in industrial robots and high-tech surgical tools and in the navigation systems for pretty much anything that moves.
So, the real takeaway here is this. By replacing a spinning wheel with a tiny vibrating structure, engineers didn't just shrink a sensor, they totally redefined how we interact with the digital world, making our tech feel intuitive, natural, and responsive. It was a completely silent revolution happening in our pockets, and it really makes you wonder, with technology this small and this clever, what new senses will be able to give our machines next?